Hello.
Or like, for example, you guys
Yes. Yes, there is caffeine in said thing.
Thank you, Patrick.
Oh. All right, so I gotta find cough drops. I'm dying right now. Anyway. All right. Alternating series, absolute convergence. So let's talk about this. All right. Definition: alternating series. Alternating series either in the form of blah or blah. Now, notice. Okay, when you're looking at this right here, it is -1 to whatever exponent, right? So if k is equal to 1, that means in this first one here, my exponent would be 2. So that is a even number, so therefore the negative becomes a positive, right? Okay, and then there's the other one where I have k is just equal to 1, right here, just k. So there's my odd number, right? So that this one's starting with a positive, this one's starting with a negative. So it doesn't say what a of k is going to be, it's just alternating in that series. Where a of k is greater than 0 for all integers, where k is greater than or equal to 1. Two examples of these are like this. Now, we considered this as alternating series because I have this piece right here where I could factor it out. I could factor that piece. So I could factor that, so no matter what that's going to factor, it's going to be a positive and negative somewhere, right? It's going to be bouncing up and down in between positive and negative. And so what we're looking for is to see if it's going to converge. Convergent or diverging. Okay, convergent, so think about it, bouncing up and down. If it's going to converge, what has to happen? The other part of this function has to do what? Because this part right here is going to alternate. That means 1 over k over here has to do what? It's got to converge. It's got to go to some number, right? It's got to converge to some number, and then it's going to be alternating, and then it's going to go to that eventually. Make sense? It's just going up and down, up and down, up and down, up and down until...
Before, when you know how it was just bouncing back and forth, and it would never touch something forever. I was just thinking of that.
Yes. Okay. Yeah. All right. And here's another example here where we have factorials to go along with this. Okay. So now, if you guys have your other notes out, it's going to be helpful because we're going to be dealing with some P series and some harmonics, and we're going to be dealing with. I can't remember. Anyway, some of the other tests that we're going to look at. So the P series one is going to be important. All right, so the numbers, if the numbers a and k, where a of k is greater than 0 of an alternating series, it's going to be like this or it's like this. One or the other, right? So satisfy the conditions. Satisfy the two conditions. So now, if the a of n goes to 0, so that's basically saying I'm going to factor out my alternating part, my -1 to the power, right? To the k or k plus 1, right? So I'm going to take that piece out, and that means my other piece of a of n, as I take the limit to infinity, as that goes to infinity, it needs to go to 0. Okay? It's going to go to 0. So that piece right there is going to go to 0. So I have an alternating times a going to 0, so that means that the whole thing is going to be going to 0. And the a of k are non-increasing. That is that each one is going to be less than the previous one. Yes? Okay, then the alternating series converges. So this is for convergent tests. So if it doesn't do this, or if it doesn't do this, then it diverges. That's the point. So if it doesn't converge, therefore it diverges. All right. Alternating series test is credited to Leibniz and is often called the Liveness Tests, or Leibniz criterion. Okay. Also, go along with this, recall a bounded monotonic sequence converges. Remember, what does the bonded mean? Bounded. Remember? Somewhere in between those two. Okay? Monotonic, that means it's going to slowly converge to something. Okay? It's going to stay within there, and it's not just going to be the harmonic jumping back and forth to those bounds.
Right.
Okay? It's going to converge somewhere there. Show that the alternating series, bleh, okay, converges. All right. Okay, so let's start the test. So let's kind of factor this thing out. So it's going to be basically A over N, right? So if I take out this, what am I going to have? Because that's my alternating part. It's going to be 1 over N, right? So I'm going to take the limit as N goes to infinity of 1 over N.
Which goes to 0.
So as N,
0.
yes.
N approaches infinity.
It goes to 0, right? So limit goes to 0. Okay. Yeah? Okay, that's good. That's important right there, right? So that was step 1 of my convergent. What was the next step?
Each term is less than the next.
Are they less than the previous? We have 1, we have half, third, fourth. Is each one less than the previous? Yes.
But the signs change.
I know the sign changed, but I'm just looking for the A of N. Because this is alternating, so remember this is going to be, so if I'm looking at a sketch of my values, so remember it started here, up here at 1, and here is basically like 0. So it starts here, and then it goes half, then it goes 1/3, right? Which is here, 1/4 here, 1. So it's eventually getting to that, right? So as I'm going with this, it is, my number's going down, 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 really, really close to 0, right? Make sense or no? Okay, so they are less than. So now, as I'm adding and subtracting this, I'm going to be at the sum of each one. Okay, when using alternating series test, check the limit of the nth term first. Nth term. Nth term, that means some number, right? Check the limit of the nth term. Okay, where the limit of n goes to infinity, A of n is not equal to 0, test diverges. Tell us immediately series diverges. For example, if testing alternating series like we have here. So if you notice, kind of take this piece out right here, right? Okay, we take out that piece there. And then from there, we're going to end up with these values. If you notice, okay, we find that the limit, A of n, goes to infinity, of A of n right here, goes to 1. So that value right there, remember if we take the limit going to infinity, they have the same degree, don't they? Yes, same degree? So that's going to be 1 over 1, which is just 1, right? The coefficient. I'm going to take the limit going to infinity, the coefficient is 1. There is no need to look further. By the test for divergent, the series diverges. So it's basically that first step. It failed the first step. Okay, does the limit go to 0? No, it doesn't, so fail. Dang, this is ugly. Okay.
It diverges, right?
Okay, so now let's go ahead and do that limit. So if I'm looking at it, it's going to be the limit of what?
2k squared plus 9 over k squared.
Limit of n goes to infinity of 2n squared plus 9 over n squared plus 1, which is just going to give me 2. So it fails my test, doesn't it? So it doesn't go to 0 because my test was right back here. Satisfy 2 conditions for it to be converges right there. So this one is going to diverge. Let's circle that. Diverge. If the limit as n goes to infinity of a of n equals 0, then check whether the terms a, k are non-increasing. Recall that the 3 ways to verify that the a of k are non-increasing. Use the algebraic difference. Show that a of n plus 1 minus a of n should be less than or equal to 0 for all n greater than 1. Does that make sense? So if I take the first two terms, right? So let's go back to that previous one because I have terms there, right? Where's that one with terms? Here we go, terms. So first two terms. So it's a n plus 1 minus n, right? So it's going to be is that going to be less than equal to 0? Yeah? Yeah. Okay, yeah, that one is right. Okay, but that's what we're talking about. So take the two terms. So, but we're not doing that test on those. I just use those numbers as examples for here. Algebraic difference, show that this is right here. So we already got that the limit is equal to 0. So if the limit wasn't equal to 0 like that previous one, I'd stop right there and just say divergent. But if I did get 0, then I have to check to see if they're increasing or decreasing. Okay, use the algebraic ratio test to show that a of n plus 1 divided by a of n is going to be less than or equal to 1. For all n greater than or equal to 1, use the derivative of the related function f defined for x is greater than 0, for which that a of n is equal to f of n. For all n, show that f prime, that means the slope of the function, right? Okay, is going to be less than or equal to 0, right? So the slope of the function is going to be less than or equal to 0, so that means it's going to be going down, right? The equation is going down. For all x, that is going to be greater than 0. Did I make sense or no?
That makes sense.
Okay. No, okay, so the limit as n goes to infinity of a of n for alternating series and the terms are not non-decreasing. The alternating series test gives no guidance. These cases, alternating series may converge or diverge. So, non-decreasing. What's the idea of a non-decreasing number? How about the number 5?
Oh.
What if it's 5, and then 5, and then 5, and then 5? Okay. So, is that decreasing? That's a non-decreasing number. It's also non-increasing, right? So, for whatever the function is, you would get the limit as n goes to infinity, we get 0. Right? Yes?
How could a function have a limit that equals 0 and be non-decreasing unless it was 0?
There's an example one here. I can't think of it off the top of my head. But there is examples of those. But that's the reason why I put it in the notes. It is possible. It's kind of like, you know, the mysterious jackalope. Yes, they're out there in the wild. They are. Okay? Bigfoot is real. Okay? I know. We're living in an illusion in the world. Anyway. All right. Show that alternating series test converges. All right. So, I kind of don't like this one. I do not like it here or there. All right. So let's try algebraic ratio test. So in an algebraic ratio test, we know that this piece right here is my alternating part, right?
Yeah.
Okay. Yeah, so we're gonna end up having, so it is, it's right here. So a of n plus 1 over a of n. So a of n plus 1 over a of n. So I'm gonna rewrite this as a of n plus 1 crap. There we go. And that has to be, I gotta make sure I'm actually less than equal to 1. I don't want to screw this one up because I forgot my notes at home.
Is there a derivative of factorial?
Yep, I did write it wrong. I did because it's, this right here comes out. So this is actually going to be 1 over 2n factorial. Right? This is my a of n. And then my a of n plus 1 is going to give me what? 1 over. There you go.
Bang.
So I did the math a little bit. I jumped way too much. So I just wanted to make sure that you guys know where these things are coming from. So I'm supposed to write it as a of n plus 1 over a of n, right? So if I do that, I'm going to do this. So it's going to be 1 over, okay, let's do, right? Okay, so I rewrote those. I put them in there, right? So I put my a of n plus 1 over a of n. I have fractions over fractions. I do not like them. So what should I do? Multiply by the reciprocal, right? So the reciprocal is going to be 1, come on, 1 over 2 n plus 2 factorial times reciprocal, which is 2n factorial over 1. Okay, I'm going to bring it down here. This is going to be 2n factorial over 2n plus 2 factorial. All right, what does factorial mean? What's 3 factorial? That's better. Start at the top. 3 times 2 times 1, right? So what do you do in each one of those factorials? In each term, what do you do to get the next term? So if I said 5 factorial,
Multiply by each integer that makes counting from 1 to that number.
or that number to 1.
Or
Yeah, that number to 1, right? That, okay, that's fine, it's good. Yes, it's, you know, but if yeah, anyway. So each time we're going to subtract 1, right? So if I start with that, so it'd be 5 times 4 times 3 times 2 times 1, right? 3 factorial would be 3 times 2 times 1, right? Okay, so now if I have this factorial, this is my first term, right? So let's see. On the bottom, I'm going to end up with, let's do these out. So it's going to be my first term is here, right? What's the next term? Two and what? Take away 1. Right? Yes?
Yeah.
What's the next term?
2n. And now we're back at our start.
Okay. And it's going to keep continuing, isn't it? So in this case, I'm going to write it like that because it's going to keep continuing. It's going to keep going and going and going. So every single time, I'm still going to subtract 1, but I'm just going to say that, hey, 2n factorial right there. So I got to that. Now what's on top?
2n.
Factorial, right?
Yeah.
So I have my 2n factorial, and I did this on purpose. I wrote out my terms, and so now what's going to happen? My factorials go away, don't they? The 2n factorial is going to go away, so I can get rid of those. So I'm going to be left with 1 over 2n plus 2 times 2n plus 1. Now, I did some algebra. I cleaned up those factorials. The factorials are now gone. Okay, that's the reason why I use this test. When I use this test right here, algebraic ratio test, whenever you have factorials, you probably want to use that because you want to be able to cancel them out. If you write them as a fraction, you should be able to cancel them out at some point. Does that make sense? I should be able to cancel them out at some point, so that's what I'm looking for. Now, back to my problem. So, what do we do from here? Come on, you guys, come on. What goes next?
Do we take the limit?
Yes, now we take the limit. So I did this math right here. I did this test so I could actually clean this up, so I could actually try to get to the limit part. So, because I can't really do much with that, right? So let's do the limit. So now, as this goes to infinity, equals 0. Okay, so now, given this information, what could I do with this right here? So now that I have that, this is equal 0. And if I don't have any values, what would I do? So I could do derivative, related function, define, okay, show that it's going to be a negative. All right, so I got that. So let's see. Do I have my values though? I do, don't I? I already have the terms of this. So since I already have the terms of this, therefore, I can say what? It's going to converge.
So the signs don't really matter
No,
now?
you're just looking for the number, the A of whatever. Because with the alternating series, you know that they're going to alternate signs no matter what.
It's because we take the alternating out from the beginning.
Yes.
-1 to the k, we remove that from it. So that way if you just take a of n, because it doesn't include the alternating, you're not going to get the negative and the positive. You just get the number.
Make sense? Okay, yes. Thank you. All right. I know. know, right? All right, so on this, estimate error for convergent alternating series. For convergent alternating series, for this, satisfies two conditions of the alternate series test. The error E of n is using the sums of S of n. So you're taking the sum of all how many numbers in the series, the sum of all those. Okay, the first nth term is approximation of the sums, series numerically less than or equal to n plus 1 term of the series. So you're trying to figure out if it's, you know, basically for this, it's going to be less than what my term is for that. All right, errors estimate given it only where applicable to alternating series that satisfy two conditions required alternating series test. Okay, here's an example. So, I'm factoring out the alternating, right? Say yes. Factoring out the alternating part. What am I left with? 1 over?
K.
Okay, 1 over k, right? Or in my case, I'm looking for, yeah, so it's 1 over k. So in that, I'm going to get, as my series, my third term, it should be the sum of those together. In the alternating, so it's going to be 1, so it's alternating, so that's going to give me a positive, so that's 1. Then it's a negative, minus 1/2, plus 1/3, and it gives me this. There's the sum. Okay? And the maximum error that I can get off of this would be n plus 1. So a of n plus 1. N plus 1. So I'm not doing the a of n, I'm doing n plus 1. So n plus 1 is going to be what? Right?
Yeah.
Okay, so give me that. So that's going to be 1 over 4. Hey, look, 1 over 4. The error is going to be less than or equal to that. But and you're estimating the sum of these. So the more terms in the sum, the more accurate I'm going to be. So the more terms, if I take this all the way to infinity, I'll get an exact answer. But infinity is not a number. So instead, I'm actually going to estimate it or round it using a certain number of terms. Okay, so now, given the 9th term, okay, what am I going to use here? So it's going to be n plus 1 is 10, right? So it's 1 over 10. 1 over 10. So my error, the maximum error on my estimate for this one right here would be 0.1. 1/10. 1 over 10, because I'm plugging into this right here. Because I factored out that alternating part, right? Am I making sense, or am I just like la la land? Question. Please speak now, because it's going to get crazy. You got a question? No? Michael? No? We good? All right, so for every single one of these, my n is going to be, so it's 100. So it comes out to be 1 over 100, so that's an error. And then this one's going to be to here. We get, 1 over 1,000. There's my error. Approximate the sum S of alternating series so the error is less than that. Okay, so you probably want a calculator for this one. Because I don't know 8 factorial in my head. 6 factorial is easy. Yeah. Is that exclamation?
Yeah. Oh, funny. 40,000.
40,000.
And then our viewers gonna see that.
Yep.
Oh, it's 1/8.
Okay. There it is right there, right? How many zeros? That's like four zeros in front of it, right?
Yeah.
Okay, so what am I going for? 3 zeros. Okay. So is this now? Is that one right there already less than? That one's closer, isn't it?
Yeah.
Okay, so now I know I need to get to that point right there. So what about 6 factorial? That's like 1 over, let me see. 30, 120, 360, 720. 1 over 720?
Yep.
Yeah. So 1 over 720 and 1 over 720 as a decimal.
0, 0, 1. 2 zeros.
All right, 2 zeros. So it's going to be there. So it's somewhere in between there, right? So basically, I just need to do what? Let's go back to the thing. What does it say that I'm supposed to be doing? Did I go too many? Okay, so now let's get some. All right, so in this one it would be what? And I think, do I have to do that last one? No, I don't do the other one. Because this one's already, because this is the, remember this is supposed to be the n plus 1. This is my n plus 1 term. So that one's beyond where I was supposed to be. So add those together. So 1, was it minus or plus? Plus?
1 minus.
Minus, okay. Plus. 24.
Yep.
There we go. So there's my sum, and that's the sum that I'm estimating where the error would be less than that number.
And we know that one is.
Yes, this is the one that's actually like, was it 0.00002, right?
Yeah.
Okay, and this one was it 3 something?
3, 2. 3.
389. Thank you, 389.
So we don't add 1/8.
This one, no. You don't add that one because that's the one that's already past that. So that's the n plus 1. That's the one that's actually beyond, so it's the sum of everything up to that point. Because if you remember, this is my error right here, right? And this is only to 3. The one that I have that is actually beyond, remember the error goes to n plus 1. I want my n plus 1 to be smaller than whatever number they give me. So my n plus 1 was this. This is my n plus 1. So this is smaller than this right here. Yes? That's the n plus 1. So I found that n plus 1. So I have to go back 1 and actually add together the sum of these things. Or these 4. Sorry. The 4 terms that we have right there. So we just add those together. So where I get right here, estimating the sum, I get a number like this. And this is the n plus 1, which gives me my error. A little bit more sense or no? Did I lose you?
No.
Speak up, you guys. Did a test on this on Friday. Okay. Absolute tests. All right, we'll do that one tomorrow. All right, don't forget, like, share, and subscribe.